Uh, the terms The term Scaling laws describes the functional relations between the characteristics of the deep learning model quality, like loss or performance metrics, and hyperparameters such as dataset size, model size, or amount of compute. Such experiments started way before the deep learning era, focusing on the popular machine learning models of that time. The empirical research on the impact of deep learning models size on performance gained a focus a few years ago. One of the most influential works in scaling laws is Scaling Laws for Neural Language Models by Kaplan and others. They found power law scaling for the transformer language models using the cross-entropy laws, which you can see on the left figure on the slide. Also, a power law scaling was developed for vision transformers by Jay and others, which is shown in the right figure. The figures represent that the loss values received during experiments marked as points closely match the values derived from the provided formulas. They are illustrated as dashed lines on the charts. Application of scaling laws is common in large language models like GPT-3 and 4. Scaling laws are also studied in computer vision, focusing mainly on discriminative models. There is less research on scaling laws for generative models in computer vision, such as GANs and diffusion models. To the best of our knowledge, the exploration of scaling laws for generative and, in particular, diffusion models is limited and concentrated mostly on the size of the model. Let's move on to the model for which we are planning to develop scaling laws. ControlNet is a neural network structure to add image-based spatial conditions to the diffusion models. Spatial conditions may include canny edges, human poses, depth maps, sketches, and other descriptors that explain the size, shape, and position of objects in the image. It can be useful when the user knows the shapes and structures they want to see in the generated image, but desires to observe them in various colors, textures, or environments. In recent years, diffusion models have attracted increasing attention. In industry, text-to-image generative models such as Stable Diffusion, Midjourney, and DALL-E have gained popularity and wide use. Similarly, the research community has shown a significant interest in diffusion models. It is evidenced by the rapid increase in the percentage of papers related to diffusion accepted at the CVPR conference over the past 2 years. Let's take a look at image generation using diffusion models. Initially, we begin with a Gaussian noise as the input image. Then the neural network predicts the noise added during the forward diffusion process. The predicted noise subtracted from the input image and we get the denoised version of the image. This process is done iteratively and after n iterations we get a cool image. Models having just a noise image as input are called unconditional diffusion models. The conditional diffusion models allow more control of the output by adding extra conditions like text, image, or color to the generation process. Let's see example on the slide. The Stable Diffusion model incorporates both the noise image and the text prompt, such as cute corgi puppy in our case, during the image generation process. In contrast, the ControlNet model not only uses the prompt, but also takes into account a special condition, specifically the canny edges of the target corgi image. As a result, the Stable Diffusion model can generate a corgi image for us, while the ControlNet model can generate a corgi in the exact pose we specify. I'm referring to the Stable Diffusion model as an example of a text-to-image diffusion model because we will specifically use it in our experiments. Now, when we have explored more about ControlNet, let's move on to the identified research gaps. Scaling laws for conditional generative models are basically non-existent. The authors of the ControlNet provided only a qualitative evaluation of the model scaling with just a single image in their paper. We aim to fill this gap with the results for quantitative evaluation of ControlNet. Upon reviewing the literature, we identified additional research gap, specifically the selection of metrics to formulate scaling laws for ControlNet. The first evident option is to use ControlNet loss function, but as we can see in the chart, it isn't much informative. Basically, it shows a decreasing tendency, but it doesn't represent if the ControlNet is learned to follow control signal. When I say control signal, I mean special condition that is used. The second option is to use traditional image quality metrics like PCNR, SSIM, fit, and perceptual loss. They can be informative for us, but similarly, they don't measure correspondence of the generated image to control signal. So we propose the first hypothesis that sounds like the conditional image generation is of good quality and aligns with the control signal when the estimated contours on generated image are the same as the control signal itself. Such alignment can be estimated with task-specific metrics. The second hypothesis is that training the control net on larger dataset size is expected to result in an improvement in the quality of the generated images. The third is there exists simple functional relationship between the size of the dataset and the performance metrics. And the fourth, the founded scaling laws are consistent across different types of control signals, such as scanning edges, segmentation masks, etc. Our goal is to formulate scaling laws for ControlNet, and the additional goal is to determine whether the scaling laws are consistent for different control signals. Now we are ready to move on to our early results. We validated our hypothesis on the small-scale dataset called FIL50K, provided by the authors of the ControlNet. As we can understand from its name, it consists of 50K examples. As a control signal, there is edge of the circle. As a prompt, there is provided color for filling the circle and color for the background. So the control net has to learn to fill in the circle with the specific edge and specific colors. For evaluation, we took metrics initially used for edge detection tasks. As a target image, we use control signal, and as a predicted, we use scanning edge of the generated image. The first metric is the average precision among all thresholds, where values of the pixels above the threshold are edges, below the threshold are background. Precision is calculated between the control signal and scanning edge, where edges equal to 1 and background equals to 0. The second metric is an optimal dataset scale, which is the maximum F1 score among all thresholds. There is results that validate our first hypothesis, namely if it is reasonable to use discussed metrics or not. The answer is yes, because the metrics clearly represent the correspondence between the predicted image and target image edges. Also, there clearly represent sudden convergence phenomenon when the model starts to follow the control signal after a certain step. You can see it as a red line on the upper chart. Despite the model started to respond to the control signal even before reaching 1K steps, it still requires further training to improve its understanding of colors. Additionally, we used blurred version of edges for matrix calculation to avoid unnecessary penalties because of minor changes in edge positions. The best possible value of each matrix is shown as a green dash line in the charts. We conducted experiments varying the sizes of the training datasets to validate our second hypothesis, namely if the larger dataset size is better. This hypothesis also confirmed, as you can see on the left chart, The bigger the dataset size, the bigger average precision metric, while the loss of the control net doesn't show this correspondence. All metrics were calculated at 3150 step, which corresponds to 4 epochs on full 50K dataset. Also important note here that all models were trained on the same amount of time and steps. The trained models were additionally estimated in a non-prompt mode to confirm whether the model truly learned to follow to the control signal. And as you can see in the image, it does. Also, you can see that the bigger the dataset size, the control net better learned the target colors. As the prediction image with the mean circle, when the model was trained on 1% of the data, which is equivalent to 500 images. Even predict other unnecessary shapes. So it's time for wrapping up. The first hypothesis was confirmed on small-scale dataset with metrics for edge detection task. The second hypothesis was also confirmed on small-scale dataset, which means that the bigger dataset size, the better edge detection metric, while the loss of the control net is uninformative. We are considering the next potential impact of our research. The findings from the proposed research project can be valuable for predicting the performance of the control net for efficient utilization of the resources. Considering the common application of scaling laws for large language models and the increasing popularity of diffusion models, the outcomes are likely to benefit both the research community and the industry. Exploring the identified research gap in performance metrics for estimating control net results opens the possibility for further investigations in other condition-based image generation models. As a future work, we are planning conducting experiments on a large-scale dataset and validate our hypothesis on it. Thank you for your time and happy to take your questions.
Thank you, Diana. Also, thank you for saving us 5 minutes of your precious time. And therefore, we may wish to, before we go to questions and answers, I would suggest that some of us, including the virtual guests, may wish to give a comment. For example, Dmitro Mishkin is with us. Perhaps, Dmitro, you would like to say something about this work and your expectations about the impact. Okay, we may go. We may go with the questions at the moment. Are there any questions in the audience, please? Igor?
Probably as for now, we don't think about it, but it's a good point. And also, while reviewing related work, we see the work about data pruning that describes what you say. They studied was concentrated that they choose the data set relying on the entropy of the images, and the results was that the better the data set was gathered and the better images, so the performance will be better than the large data set um, with some images that we don't know what they mean and etc. So probably if we have time for it and resources, we will concentrate it on it.
More questions? Okay, thank you very much. Let us switch to the next speaker. Our next speaker is Anton Brajny. Could you please connect to the session and share your screen? Okay, thank you. I'm happy to introduce Mr. Anton Brajny with a talk entitled Few Shot Support-Based Object Counting. This work has been advised by Konstantin Bohan. So, Anton, the floor is yours. Please go ahead.
So object counting is a task of estimating specific object entities, the number of specific object entities present in an image, and it has diverse applications spanning multiple domains, from traffic monitoring to retail analytics and inventory management. On the right side of the slide, you can see images with different boxes, pallets, and containers in some warehouse. And the task is quite simple, just to count them. This is an example of applying object counting in logistic domain. But the major problem is that this warehouse often receives new kinds of boxes and containers, each having different shape and appearance. And also once in a while, a completely different item may appear, say like bags or pipes. So we need not only to be able to count the number of objects, but we have to take into account the following factors. The first one is data scarcity. For many tasks, there is simply not enough training data available to train a robust model in a traditional manner. The second one is cost and time for annotation. Even if we have enough data, it still requires time and often, or should I say, almost always money to annotate it. And in our example with the warehouse, we would need to additionally annotate data for each time a new object class appears. So based on this, we formulate the goal of the research project as following. We want to develop a robust object counting method, which can be scaled to a large number of categories. can be applied in various domains and doesn't require an extensive annotation. Sorry. At first, we considered weak and semi-supervised methods due to their ability to leverage unlabeled or less precisely labeled data. But unfortunately, they still need at least some amount of annotation and training to be able to work with new object classes. So we chose to focus on completely class agnostic methods, in particular, zero-shot and few-shot. Okay, so the first group of methods which we have reviewed are called few-shot patch-based methods. On the slide, you can see a typical high-level architecture of such method. The image is passed, we pass a query image and additionally annotate a few bounding boxes around the object of interest which you want to count. These bounding boxes go through the region of interest pooling or some similar pooling layer to extract object embeddings. And these object embeddings are cross-correlated with the image features. The resulting correlation heat map is then refined to a density map, which is our target. And in this case, the final object count is just the sum of the density map. Surely we can use an object detection approach and just simply count the number of detected instances. Some methods definitely do that, but object counting doesn't require knowing the exact location of the objects, and it's just redundant information for the model to learn. Also, density map usually works better under heavy occlusion. So back to this method, patch-based methods has one major problem in its design. We need to manually annotate each new query image, and it means that using this method in real-world systems is impractical, and it would definitely not work in our example with the warehouse. Another group of methods we have reviewed is about text-guided zero-shot methods. They utilize a multimodal model like CLIP, in which text and visual embeddings are aligned. So instead of annotating patch exemplars, we are simply providing a name of the object or its description, and its embedding is then later used in a similar way that we discussed before with the patch-based method. This removes the need for manual annotation and seems like a perfect choice for us. However, textual descriptions can be ambiguous, and in our example with the warehouse, it would be really difficult to differentiate between different kinds of boxes and palettes. On general, text-guided methods perform worse than visual-guided ones. And the third and final group of methods are so-called few-shot support-based methods. They rely on visual exemplars or prompts to identify the object of interest, but unlike patch-based methods, they do not require manual annotation. Instead, they used a support set to extract the information from the object, about the object. We identified 3 variants of these support-based methods. The first one uses another reference image depicting the object of interest, which we call an external exemplar. The second one is called cross-image counting, where we can annotate bounding boxes in one image and use them to count the objects of the same class in another one. And the third one involves passing an input pair of passing a support set in the form of a pair input target, which serves as an example for a model. Okay, so by the way, support-based method, the term support-based wasn't adopted in the literature before, at least in the object counting domain, but we needed some way to refer to these three methods. Another way would be to refer to them as those which use external exemplars prompts, meaning that these prompts are not a part of the input query image, unlike the internal prompts in patch-based methods. So these support methods, as I said, do not require manual annotation and because the support set can be prepared in advance and only one for one image class. And it provides a more direct visual comparison between object exemplars and the features of the query image compared to the text guys methods. So seems like a perfect choice for us, but unfortunately, this approach is not well studied. There were very limited amounts of research was done in this direction. To the best of our knowledge, there are only 3 works on support-based methods, only one for each of the 3 variants we described before. And actually, only one paper was published. The other 2 are just preprints. Also, these papers do not share designed architecture details in sufficient details. And these support-based methods are not directly comparable to the patch-based or visual guided ones because they were trained and evaluated on a completely different custom data sets that were represented in those papers, but never shared. So patch-based and visual guided methods, on the other hand, are trained on the same publicly available datasets. So what datasets are there? The main benchmark and the first one few-shot counting dataset is called FSC 147. The main problem with it is that its images are with simple scenes with predominantly with one object class. So the model can easily identify which object it needs to count. And also it is quite small, slightly more than 6,000 images, and doesn't cover enough domains as it contains only 147 classes. And if we take into account the train test and validation splits, the model has even less data to learn from. The second dataset is a subset of LV's object detection segmentation dataset. It was specifically designed to solve the problem with simple scenes of FSC 147. It contains images with several object classes and various backgrounds. And the third dataset actually was presented only a few months ago, and it is referenced only in one paper so far. But it is much larger than the first 2. However, not most, but many of its images are almost identical or depict the same object class. Yeah, here you can see the sample images from FSC 147 and LV's datasets showcasing the difference in the complexity of images, simple scenes with one object class and complex scenes with several object classes. And here are sample images from the third dataset, CA44, count anything. On the left, you can see almost identical images depicting the ship. And in fact, these images comprise almost 10% of the whole data set, which is a lot. And on the right are example, you can see that some images are just mosaics. Why is it bad? Because some parts of these mosaics can be repeating across different images, and these images, well, can be sort of as semi-duplicates, some sort. And another issue, and the final one we want to discuss, is actually the current performance of class-agnostic methods. The current best performing state-of-the-art few-shot methods has an mean average error of about 10. If we take into account that the average number of objects in an image is about 100, the error is roughly 10%. To give you an idea, the traditional object counting, the traditional supervised object counting methods have an error of about 1 or 2%. We think there are two reasons why the performance is this low. The first one is the data set. It's really small and, as I said, contains not enough classes, especially for an object counting for a few shots task. And the second reason are the models. We're not talking about the architectures, but the backbones, especially their sizes. All of these methods use either ResNet or some small visual transformer. And we believe these kinds of models cannot output features that are good enough for a few-shot task. So what do we propose? First of all, we need a larger data set. We plan to combine the existing 3 ones and extend them with new images. The second idea is to design a new few-shot counting architecture capable of efficiently processing external prompts. So basically working with support-based prompts. And also explored the adaptation of foundational computer vision models as a backbone. Yeah, so early results. We have already combined the existing datasets into one. We have identified and removed the duplicate images, also renamed and combined similar classes for consistency, and also collected about 1,000 images in the domains that we were interested in, specifically logistics and industry, and extended data set with it. The combining dataset comprises about 35,000 images and 467 classes. And it covers many various domains, including logistics, industry, medicine, retail, and others. We have also begun testing different foundational computer vision models as backbones. In particular, we compared the self-supervised Dino and IJEPA and the encoder from the segment anything model. In theory, a self-supervised method should have better features, but they are not suited, not designed for the dense prediction task that we have. And as you can see on the slides, Dino and IJEPA have blurred density, predict density map, and struggle to differentiate small objects. Efficient transformer from segment anything model, on the other hand, was specifically designed for dense prediction tasks, and so it works much better and much faster, by the way. Oh, sorry. Okay, so concluding remarks, we have compared existing class-agnostic counting approaches, analyzed research gaps, and proposed the identify the areas for improvement. We have combined and refined existing data sets, and currently we are testing different support-based architecture modifications. The main one and only pain point that we have is that training time, especially those training models, especially those utilizing foundational computer vision models, takes quite a long time. So it limits our ability to quickly experiment. That's the end of the presentation. Do you have any questions?
Thank you, Anton. Do we have any questions? Just retranslate. Mike, keeper.
Thank you for your talk. My question will be regarding the, like you were saying about pre-trained models, that you're taking pre-trained feature extractor like here and in previous slides, like where you have related works. So basically, you have the pre-trained feature extractor that was trained on the ImageNet Lion dataset, whatever. So large scale, common context, image dataset. So how this approach would scale if we would go out from this domain and we will go, like, let's say, to satellite imaging, and we want to count something from the top view, or we are going on the micro level and we want to count nucleus in cell. Like, will it work, or like will fail?
The backbone itself is frozen, is freezed, so we do not fine tune it in any way. The main parts of the network is the head, and it is actually designed to work with any domain due to its few-shot nature, and also, as I described, sorry, data set actually comprises many different domains. You mentioned biology, some nucleus. It contains those kinds of images as well. Maybe not satellite, but I guess if we consider those extreme cases, we can slightly fine-tune the head part of the architecture.
My question was regarding the like you have the data set that you train on, this one that contains common context, nucleus, whatever. So, and if we want to scale it to the new domains, we will need to fine tune it again. Yeah, and it's not few shot. Basically, we need to pre-train it and then to use few shot to later on retrieve the results.
Well, I think it would work even without fine-tuning. I'd say it would work better than a regular, some traditional supervised approach. Few shot definitely would increase the accuracy. Maybe you would observe some performance drop, but I don't think you would need to train and fine-tune your model for any new domain that's not in this data set. Only for, as I said, some extreme cases like satellite images that are not that have a distribution very different from the original data set. But I think the nature, the few-shot nature should be enough for this task.
Okay, thank you.
More questions? Okay. Ruslan?
Maybe one question from my side. As we touched the topic of the data set and different proportions of different types of data, how are you going to use this data set? You just concatenate all the data sets together, or will you later fine-tune on this small 1,000 in-domain images of the logistics images or?
We concatenated the existing 3 data sets and also extended it with additional 1,000 images. And we'll train on this whole data set with 35,000 images. All the duplicates images were removed, and we also, as I said, combined classes. Well, some classes in different data sets might have different names, but we fixed this issue.
Yes, and I have a little bit more context than others because I also organize master seminars. So during the last seminar, you showed also the example of using augmentations, but you
Yes.
didn't include it into your presentation.
Yes, well, it wasn't included in the paper, positional paper either, and it's mostly related to the patch-based methods where we explicitly augment those exemplars. So I didn't mention it during this presentation, as it covers support-based, focused on support-based domains. But I think we can extend and use the segmentations not only on the exemplars, but on any of the objects in the image.
Okay, got it. Thank you.
More questions? Okay, I have one. Could you please return back to back to the slide which describes your data set and domains? No, next one. I just noticed that the data set is not really balanced in terms of the instances per domain. Do you expect that it will be demonstrating equally good or equally bad performance based on this disbalance?
Regarding these domains, this is like an arbitrary categorization. Actually, what I did was to take all the class names that dataset has and used large language models which identified the most common, I'd say, domains or categories. So maybe some of them are overlapping or can be further split into more equal segments, I say. But no, I don't think it would. I don't think it implies that model would perform worse on, as say, tools and equipment domain, which comprise a small part.
Okay, thank you. Igor?
Yeah, I have one more. Could you please go to the slide where you compared Dino versus IJEPA? Yeah, here. So as far as I can see here, you're using WIT-H and EfficientNet with L2. It's quite large model. So my question is regarding the next one. From your presentation, I understood that you plan to use this model in logistics and in the real world applications. So it should have like good performance on edge devices or somewhere else, and you will not place there a GPU for the processing of the images. And if you're comparing such huge backbones, probably you need to consider moving down in development of your own model to consider that you also need to have like constraints on the performance.
Yeah, I got the question, but yeah, I agree that Dino and IJEPA, so those regular vision transformers are quite large and not designed for, cannot be efficiently used in real world systems, but efficient transformer, on the other hand, can be used even, can be efficiently used on edge devices and has an inference of less than a second. And in fact, come back to the first slide. Sorry. No. These images are from a real-world counting system, and it has basically a GPU installed on it. So even if it's edge, it doesn't necessarily imply that it can be CPU only.
Yeah, so it's quite powerful edge, I would say. Thank you.
More questions? Thank you very much. The next speaker is Katarina Karpov. Next to the session. Anton? Could you please? Yeah. It's my pleasure to introduce Katarina Karpov with her talk on 3D room layout estimation from RGB images. This work has been done in cooperation and advised by Denis Rozumny. Yeah, I can make any stop you wish. Just let me know where to start speaking. Ja, blir muted, isn't it? Yeah, let's go ahead. And get the questions ready. Doesn't connect? I may wish to share the whole screen. Coming, yeah. The team is really thankful to the previous speakers for saving time for technical issues. Okay, now? Okay. So let me just repeat. Katarina? I'm delighted to introduce Katarina Karpov, who has just successfully resolved all the technical issues with the help of her TA. The work is on 3D room layout estimation from RGB images. And this project has been advised by Denis Rozumny, Computer Vision and Geometry Group, ETH Zurich. So, Katarina, please go ahead. The floor is yours. 1-1.
1-1. Hello, everyone. It is a pleasure to be here with you today. I am the primary author of the position paper presenting our project. Our focus lies in advancing spatial analysis, particularly in the realm of 3D room layout estimation from RGB images. This work advised by Denis Rozumny from ETH Zurich. The plan of my talk is the following. We start with introduction and motivation and research goals. Then about the outcomes of the related work analysis section, reviews related work in the field, and show recent advancement in 3D room layout estimation. In research question and problems section, we outlines the main challenges that was in existing researches. Planned approach to solution section details the methodology by intent to adapt moving forward. Early results section presents our today's results. "3D room layout estimation is a transformative technology at the intersection of computer vision and artificial intelligence. It involves the process of creating a three-dimensional representation of interior spaces, detailing elements such as walls, floors, ceiling, and the placement of the objects within the room. The sophisticated representation is not only about visualizing space, but understanding it, allowing computer to interpret and interact with our physical world in a meaningful way. Here is about our motivation. Imagine being able to map out the entire layout of room without nothing more than a simple video captured from your smartphone. This vision drives our research into 3D room layout estimation solely from RGB images. In today's world, where the accessibility of technology is as crucial as its advancement, our motivation is clear: to make spatial understanding and interior mapping not only more advanced, but also universally accessible and cost-effective. So we just use RGB videos without depth sensors and any other imaging technologies. The implication of 3D room layout estimation widely used in many applications such as interior design, real estate visualization, robot navigation, augmented reality. Based on the application requirements, analysis of the related work in the field and identified research gaps, the research goal of our project was set as follows. Our research aims to create and validate an innovative pipeline that automatically predicts 3D room layouts with high precision and adaptivity. Below you can see GIF. The GIF you see is one of the ground truth sense from CADIState dataset. We use this dataset for our project. At the output, we expect something similar that was on the GIF. Related work and history in this domain started with geometry-based approach. And this approach are utilizing geometric pipelines principles to interpret the spatial configuration in indoor environments. These methods fundamentally rely on the analysis of vanishing points where the convergence of parallel lines is in the image provides insights into the room's orientation and depth. Essentially, to these geometric methods are edge detection and line segmentation, which serve as a foundation for structural analysis. These techniques are pivotal in governing the layout of rooms, yet they face limitation when confronted with cluttered environments, occlusions, and non-orthogonal architectures that diverge from the Manhattan world model. And Manhattan world model is some approach that proposed by Coghlan, which posits that sense consists of three-domain orthogonal orientation with wall perpendicular to each other and to the ceiling and floor. The next approach that widely used nowadays is hybrid. It uses a combination of deep learning with early geometry-based approach. It integrates machine learning and deep learning with geometric principles and revolutionize room layout estimation from RGB images. The first approach that I would like to describe is Li et al. His approach focused on key point localization. Their method simplifies the process by directly identifying critical points and room types, which are then connected in a specific sequence based on the room type to create the spatial layout. They utilized a convolutional encoder-decoder architecture with which facilitate effective semantic segmentation of the room layout surface. And the next is Wang et al. He predict coarse position of case point and refining coordinate points coordinates by aligning them with the nearest image boundary. The main limitation of these two approaches is that they limit choice of room layouts that can be estimated. It's only 10 types. The next one approach in this hybrid methodology is generate a 3D room layout estimation from Panorama, and it is I with my advisor decided to test it using HorizontNet convolutional neural network, and the result was really bad because it's hard to generate panorama from video. And also these approaches are bad for our projects because they find these corners, edges, walls, etc. in 2D and then generate from this 3-point clouds. So a significant limitation of many current approaches is they are based on cuboid shaped and general Manhattan room definition, while practically these methods lack the flexibility to accommodate the diverse and complex geometries found in the real-world scenarios. Many approaches rely on this Manhattan word and cuboid room approaches. Also, most of all recently made researchers worked with single images or panorama, and as I said before, they map this 3D, they map room layout in body and then transpose it to 3D, and we would like to give the solution. It is data-driven approach, and our new released CADIstate dataset that's full of various room plans. We would like, as an input data video, and we would like to work in 3D space and estimate room layouts in 3D space. So our research question is, can we create an efficient machine learning pipeline to automatically predict 3D room layouts from RGB images? Is it possible to effectively predicts 3D room layouts from RGB images automatically using PointNet for segmentation and RunZack for plane fitting. Can our new released CADIstat dataset improve accuracy and reliability? Can our model work good with unseen data and in real-world environments? And how our model will handle with non-standard and irregular geometries? So we are challenged to work with RGB videos without additional depth sensors, intrinsic and extrinsic camera parameters. Also, we decided to work in 3D space, and the research problem attacked in our problem is to develop the component solution that positively answered our research questions. We decided to work with new released CADIstat dataset that was released by my advisor. So CADIstat dataset is uniquely comprehensive in its provision of detailed 3D annotation for a wide array of complex multi-object RGB videos. It contained 2,246 videos, and it's pretty good in this area of room layout estimation. So approach to solution, we decided to start with data preparation and pre-processing. We use Colmap to find this intrinsic metrics and camera position and orientation in the world. Also, we decided to use multi-view depth map generation to generate this depth map. It is necessary to use it because it helps us to reconstruct this 3D space. Also, when we made this depth map, based on it, we make a 3D reconstruction. It is 3D mesh, and then we convert it to point cloud because we decided to work with point clouds. So here is the main difference between point clouds and the 3D mesh. Point clouds are a collection of points in space representing a shape in a more raw and unstructured form. 3D meshes are a step further in the process where the shape is defined by a network of interconnected triangles providing a smooth renderable surface. Each has its use depending on the needs of the project, with point clouds being closer to the raw data from 3D scans and meshes being more suitable for finalized, visually completed 3D representation. I want to anticipate your questions. Why doesn't NERV? So the main reason is computational resources. To use point clouds can be less computationally intensive than train a NERV model. Also, it's model train and overfitting. We have only nearly 3,000 of reconstructed stands, and it can be it can handle overfitting for models like NERV, typically. Also, we work to make real-time application, and point clouds can solve it because it's a really light model. We can make a really light model to work with point clouds. And level of detail, we need to find only cells, floor, etc., and we doesn't need much details as a NERV reconstruction present. So our approach in model development section, we would like, as I mentioned, work in 3D space with point clouds. So we use PointNet as our main deep learning model for segmentation. And after that, we use Renczek for plane fitting. About our evaluation metrics, the performance of estimation of room layouts can be measured with standard evaluation metrics that widely used in computer vision. It's intersection over union, pixel accuracy, and root mean square error. Also, we would like to compare our results with existing methods, and we would like to make a real-time project, so it should to work really fast and efficiency. And early results. Firstly, we had reviewed the relevant thought and current commercial technology and solution offerings. The results of this review represented in our position paper in second section. We have outlined a work plan and make some suitable technicals and would like to make some suitable technical solution. And also as a first milestone, we create a pipeline to generate 3D reconstruction from RGB images. So we prepared our data set for model learning. Thank you for your attention.
Thank you very much. Do you have questions? Igor? No? Okay. 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 While you're thinking about your questions, I'll try to raise mine. And for that, I would really like you to go back to slide number 3, please.
Is it about introduction?
Yeah, it's about introduction. You just mentioned here in this context that 3D room layout estimation lies in the intersection of artificial intelligence and computer vision. Could you please draw us this intersection?
Okay.
Well, the reason to ask is that I to think that computer vision is just one of the fields in artificial intelligence, so it may lie within artificial. So what is the intersection? Why to mention artificial intelligence?
Okay, maybe it was my fault. I think that I mean artificial intelligence, that we can not only geometric based approach from computer vision use, but also deep learning and machine learning models. And artificial intelligence means that particularly we can use
So you
deep learning models.
You mentioned the computer vision approaches which do not relate to artificial algorithmic approaches.
Oh, okay. I understood what you mean.
Okay, good. So my second question is out of curiosity. Could you please go to your Manhattan's world slide? Yeah, this one. I'm really curious if we all know why Kuglan called it Manhattan world. Do you have an idea? What was the reason for him to call it Manhattan?
No idea. I just read research and not from historical.
Have you ever seen satellite images of Manhattan? Go to Igor and ask him. He has. The reason is that Manhattan is the most popular example of a block structure of rectangular blocks. If you look at Manhattan in a 2D projection. And therefore, all the roots are like that, with square blocks, or almost square blocks. And yeah, yeah. This is what I'm asking, because okay. And what else? This is not a question, but rather a soft recommendation for you. You mentioned several times that you and your supervisor or advisor decided to follow this or that option without explaining your rationale about the choice of this or that option. This sounds a little bit naive and not really justified, so you please avoid saying that way at the meetings where your fate might depend on the decision of the audience. So this is it from my side. To have a question?
Yes, I have like a quick question. Could you please go to your early results section? So yes, so I guess the audience from the presentation could understand that this pipeline consists of multiple steps, multiple pipelines, and it's probably not that easy to make everything work together. So I just wanted to ask you, Katarina, to kind of briefly describe these results. What does this mean? What is understand what's already achieved, and how this can help you move on?
Okay, as I said, we decided to work in 3D space because we hope that it can improve accuracy and improve our results. So till today we made this 3D reconstruction. It's hard to make because we have just videos from YouTube and in our data set, and we need to know a lot of these camera parameters to know from which side this was just made, these photos, these images. For this, we used Colmap to generate these parameters. They not always generate in good quality, so we made this camera parameters correctness. We made this SFD reconstruction to see how these parameters work together. After this correction, we made this depth map images for whole video. And based on these depth maps, we generate these 3D meshes, and then it easily to correspond it to 3D point clouds.
So do I understand correctly that when you say that you implemented a 3D reconstruction from RGB images, so in other words, you take RGB images and input, you do some magic, and you get a point cloud as an output, or what you get as an output?
It was made in format of pipeline with Docker containers. So if you can tell that Docker containers is something like magic, yes, it can be. It's three separate.
Yes, I understand, but I just mean you take RGB as input, sequence of RGB as input, and you get point cloud as output, right?
Yes, you're right.
Okay, good. Cool. Yes, thank you.
Yeah, thank you for your talk. Could you please go to the NERF slide? So you built the quite sophisticated pipeline that involves many building blocks and wires. So that optimize not end to end. So you have like one block, you have point net, you have something else. So NERF is like single pass. And like what's like, I understand that you have computational constraints, etc. So how do you think? Would NERF perform better, or like in the single way, or no? And what's the trade-off in this? Like,
Okay.
what's the resource could be used here, and what's the resource are you using, and what's the accuracy you'll get from this method, and like what's the benefits?
Okay, maybe when we forget about computational resources, it can work well, but as I said, it can handle to overfitting because we have really small data set for NERV architecture. But really don't know if we will have more time and our point clouds architecture give us bad results or not good results, we maybe will try these NERV architectures.
So basically, the limitation of NERV, not resources, but more like rather overfitting and
Yes,
not a
you're
lot of
right.
data. Okay, got it. Thank you.
Questions? No. Thank you very much. And this concludes our first session for today. So we're free to go to a coffee break, which waits for us as far as I understand. So enjoy your coffees and interaction.